Welcome back, folks. So we're looking at question number 9 from homework 19. All right, so there's a lot of things you're asking us here, but the first thing you want us to figure out is where's my function increasing and decreasing. All right, so to do this, whenever we're looking for increasing the intervals of where the function is increasing and decreasing, remember, we just take the derivative of that function. So we take the derivative of this original function, and right now we should be experts on taking derivatives. So once we do that, let me just write the answer. We get 6x x squared minus 3 squared. So again, the process is what's important. So what we did is we took the derivative of this. We used the chain rule. And then we set that derivative equal to 0. All right. And what this is going to give us is our critical values. So we go ahead and we separate each one of these pieces, set this equal to 0, and set this equal to 0. So we have 6x, we have 6x equal to 0, so therefore x has to be equal to 0. And then you set x squared minus 3 equal to 0. And some people are going to ask, well, what about the squared? Well, for this to equal 0, all we need is the inside to equal 0, because 0 squared is 0. So once the inside is 0, then we're good. This whole thing will be 0. So again, all we need is, when is this inside equal to 0? So we solve that. We add 3. We add 3. And you get x squared equals 3. All right, take the square root of both sides, and you're going to get two answers. X equals plus or minus the square root of 3. All right, so go ahead, look at that, copy it down. And let me shrink that, give us some space. All right, and what I want to do, I don't know exactly where square root of 3 is, so I punch that in my calculator, and it's approximately, I'll just say 1.7. Let me just double check. Excellent. And again, this is going to give us our intervals. So I got 0, and don't forget the plus or minus. So we got somewhere over here negative 1.7, and somewhere over here positive 1.7. All right. So this is where our graphs got split into these intervals. And then what we did is we did test points. This is where you plugged in numbers in these intervals. So this is just like the previous homework number 18. Except this one seems like a much longer process because they're asking us more questions. So we pick a number over here to plug in. So I'll plug in into f prime, I'll just plug in negative 4. You could plug in any number as long as it's to the left of negative 1.7. So I just chose negative 4 to show you. All right, so if I do that, I'm going to end up with a big negative answer. And I don't care what my answer is, as I told you before. I just want the sign. So this, I'll do the negative region. I'll shade the negative region in red. So the red is going to represent the negative interval. So that interval is negative, which tells us that f of x, the original function, is going to be decreasing in that interval. We go ahead and we pick a number between 0 and negative 1.7. So let's go ahead and let's pick negative 1. So I plug in negative 1 into f prime. So that negative 1, we plug it into f prime. Make sure you make notes of that, right? So you plug it into f prime. So negative 1 there, negative 1 there. Plug it into your calculator, and you're going to see you get, again, a negative answer. You'll get negative 24. We're not too concerned about the actual number. We just want the sign. Since it's negative, we designated red to represent that it's decreasing. So that side is also decreasing. All right, let's pick a number between 0 and 1.7. So let's just go ahead and plug in positive 1. So we plug it into f prime. So we plug in the 1 right there. Wherever we see x, we're plugging in 1. All right, plug that into your calculator, and what you're going to see is you get a positive 24. All right, so you get positive. I don't care what the number is. It's positive. So the positive, I'll just shade in blue here. So that interval right here, what's in blue, is going to represent where f of x, the original function, is increasing. And last but not least, we need to pick a number here in greater than 1.7. So I'll just plug in 4. Plug in whatever number you want. I'll just plug in 4. And so when I plug in 4 into my calculator, it gives me a positive big number. Again, we only care that it's positive. So this is the positive region. So there in that interval, f of x is also increasing. All right, so now we know where f of x is increasing and where f of x is decreasing. So let's go ahead and let's write that out. So f of x is increasing. Oops. Let me write it up here. F of x is increasing, right? And we know it's increasing whenever our interval, when we plugged in these values, they give us a positive value. All right, so whenever we got a positive value, so we saw from 0 to square root of 3. Actually, let me be consistent with the color coding system. So from 0 to the square root of 3. And you might be wondering where that square root of 3 came from. That's what this was, right? The 1.7, that was the square root of 3. And when x was greater than the square root of 3. All right, so that's where our interval is increasing. I should have wrote that in blue since we said increasing is in blue. And then we're looking at where's f of x? Where is it decreasing? And so we see it's decreasing from here to here, from negative 1.7, negative square root of 3 to 0. So negative square root of 3 to 0. All right, that's one of our regions. And over here as well. And it's an and statement, so I could write in any order I want. So when x is less than negative square root of 3. All right. And so that's one of the questions they ask. Where is our function increasing and decreasing? And I want you to also take a look here. Notice where the function f of x changes from decreasing to increasing. So everywhere over here it's decreasing, it's decreasing, it's decreasing. All of a sudden it hits 0. And to the right of 0, now our function starts to increase, increase, increase. All right. So notice the function is going down, 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 and then it goes up. So this point right here is actually a relative minimum, right? And we've discussed that in our notes. When our graph goes from decreasing to increasing, this is a relative minimum. Let's write that down. So this guy is a relative minimum. And to figure out what that actually is, what you would do is you would plug that number in, that 0, into your original function, which was 0 squared minus 3, and then you would cube that. And you would punch that into your calculator and you get negative 27. Let me shrink all this, or move it. So that point 0, comma negative 27 is a relative minimum. All right, so far, all we talked about is where our graph is increasing and decreasing. And we actually found a relative minimum. All right, the next part of the question that they ask you for these is the concavity. So for the concavity, what we're gonna do, and they want relative extrema and inflection points. So for concavity, what we do is we take the second derivative. All right, so I'll give you guys a second to copy that down or to press pause, and then we'll dive into that question. All right, so let me start a new page. All right, so what I'm gonna note is, let me bring back our derivative, which was 6x x squared minus 3 squared. And notice what we want. We want the second derivative. We want to take the derivative again. All right? And like I told you earlier in the semester, we're going to be taking a lot of derivatives. All right? So here we're going to have to use a product rule. We're going to have to use a chain rule. All right? So we end up with 24x squared times x squared minus 3, and then plus 6x squared minus 3 squared. So go ahead, and when you do all this by hand, this is what you get. I kind of kept track of stuff in my head because I noticed when I brought the 2 down, that was going to give me 12. And when I took the derivative of the inside, that would give me another 2, and that would make that 24. But again, just write everything out. Don't try to do it in your head. So just take the derivative of this and lay everything out. All right, don't take any shortcuts. All right, so we take the second derivative. That's the big point here. We've taken derivatives before. All right, now that you take the second derivative, what we're going to look at, once you get to this step, is we're going to see, what can we factor out? So check this out. Let me highlight what we're going to factor out. From 24 and 6, what's the GCF there? Well, the GCF is, and I'll do it in green, is 6. All right. Next, I look at the x values. This has an x. This doesn't have an x. Right? You might have many. So we can't factor out x. Now let's look at the x squared minus 3's. This has an x squared minus 3, and this has an x squared minus 3. So let me highlight that. This has an x squared minus 3. This has an x squared minus 3. So what you do is you factor out the smallest exponent. This only has one of them, right? This one has 2. So what you do is you factor out the smallest x squared minus 3. All right. So that's what they have in common. Now, let me write down what's left over. All right. So what is left over? Let's figure that out. So 6 times what gives us 24? Well, 6 times 4. Notice this piece had an x squared. Did we take out any x's out here? No. So it still has an x squared. It had an x squared minus 3. You factored it out. So this no longer has an x squared minus 3. You factored it out. Essentially, you canceled it out. Okay, plus. Let's go ahead and write plus. So 6 times what gives us the 6? Well, 6 times 1. You don't have to write the 1, but I'll do it. And notice, this had how many x squares minus 3? It had 2 of them, right? But you took one of those x squared minus 3's away. So you factored one of them out, but it had 2 initially. So it still has 1 x squared minus 3. It still has one of them. All right. So let's go ahead and let's combine our like terms, right? If I distribute the 1 doesn't change anything. So let's go ahead and combine our like terms. All right, just so we could clean things up a little bit. So this equals 6 times x squared minus 3 times, we got a total of 5x squared, right? Because you got a 4x squared here and a 1x squared here. So you have a total of 5x squares. And then that minus 3 is kind of just hanging out. All right, so a lot of algebra that we're doing here. And now that we've cleaned things up, remember this whole thing, we want to set equal to 0. All right. We want to set all this equal to 0 because now what we're looking at is we're looking at our concavity. All right, so we're looking at our concavity. So when we set equal to 0, what this is going to do is this is going to help us create those intervals, find those intervals where the function's concave up and concave down. All right, so let's go ahead and we set the 6 equal to 0. That's one factor. Okay, that doesn't make sense, so we cancel that. You set the x squared minus 3 equal to 0. Solve for x there. And I think we already did that upstairs. And then the 5x squared minus 3, you set that equal to 0. All right, so let me move all this. Shrink it, move it up to the side. All right, so let's go ahead. We already know for this one, we did it in the previous step. X is going to equal plus or minus the square root of 3. All right, we're going to get two answers. This one we haven't done yet, so let's solve it. So plus 3 plus 3. So we get 3 equals 5x squared. Divide both sides by 5. And you get x squared equals 3/5. All right, we're going to go ahead, take the square root of both sides. When you take the square root, don't forget, you get a plus or minus. So x is going to be equal to the square root of 3 over the square root of 5, plus or minus. We don't want our denominator to have a radical. We don't want it to have a square root. So what we do is we multiply both top and bottom by the square root of 5. All right, you rationalize that denominator. So you get x equals plus or minus the square root of 15 over 5, right? Because the square root of 5 times the square root of 5 gives us 5. So while you're copying that down, let me punch that into the calculator. The square root of 5, or sorry, square root of 15 divided by 5. So that gives us about 0.7, I'll just say 0.8. So it's approximately plus or minus 0.8. And that's just going to help me when I create my intervals. So once again, I have to plug in numbers. All right, so we're going to plug in numbers. These points are going to help us create our number line. So let's create our number line here. So we got our number line. I have negative 1.7 and positive 1.7, right? That's what the square root of 3 is, about 1.7. That's what we said earlier. So negative 1.7, positive 1.7. Then for the second equation, we got plus or minus 0.8. So I got negative 0.8 and positive 0.8. So those are going to be our, help us create our intervals. So those are going to help us create our intervals. All right, I'm copying that down. Let me group these. Let me make it wider. All right, so now that we have those intervals, remember we're taking the second derivative. So what you're doing is you pick numbers and you plug it into the second derivative. So I'll plug in, I don't know, -4. And again, I'm just choosing any point that I want and I plug it in to the left of negative 1.7. All right, so when I do that, I notice I get a positive answer. Plug that into my calculator. I'm going to plug in another number between negative 1.7 and negative 0.8. So the nicest number I could think of plugging in is negative 1. All right, when I plug in negative 1 into my calculator, I get negative 24. All right, so, oops, that's fine, that's negative 24, but the only thing I care about is that it's negative. All right, between negative 0.8 and positive 0.8, we plug in 0. When I plug in 0, I get a positive answer. And then I plug in a number that's between 0.8 and 1.7. So I'll say 1. So I'll plug in 1. F double prime, I'll plug in 1. And plug that into my calculator. And the only thing that I care about is that it is negative. So I have all those test points. And then plug in a number greater than 1.7. Plug in any number that you want. So I'll plug in positive 4. And remember where you're plugging all these in. Let me bring down the original function so you could see. You're plugging all these in to the second derivative. So wherever you see x, that's where I'm plugging in all these numbers in my calculator. Don't do this by hand, it'll just take too long, right? So I'm just relying on my calculator. Wherever I see x, I'm plugging in these numbers. And the only thing we care about is if it turns out positive or negative. That's all we're looking at. All right, and when we plug in 4, I do it in my calculator, we get a positive. So this gives us a positive value. And now, wherever we get the positive values, let me highlight those. What that tells us is that in this region, right, it's concave up. Right here, our graph is concave up. Right here, our function is concave up. And wherever we've got negative, right, our graph is concave down. In that interval, concave down. And so now we have all our intervals, right? You could see from negative infinity to negative square root of 3. And from, what was this? Square root of 15, negative square root of 15 over 5 to positive square root of 15 over 5. It was concave up. And from this was a square root of 3 to positive infinity, it was concave up. So as you're kind of doing this homework, I would kind of press pause at every section to make sure you understand the big idea, because there's a lot going on here. These problems are very lengthy because there's a lot of work happening here. And so remember, we're looking for also these inflection points that we found. So these are also called inflection points. So go ahead and write that down, because they also ask you to find inflection points. And so what you're going to be doing with these numbers, square root of 3, negative square root of 3, positive square root of 3, negative square root of 15 over 5, positive square root of 15 over 5, you're going to be plugging these into your calculator. And also you're going to be plugging them into the original function, into f of x. And those are going to give you your inflection points. All right. And they are going to come out messy. So for example, when I plug in f, notice I'm plugging into the original function of square root of 3. When I plug that into my calculator, again, I'm not plugging it in right here. I'm plugging it into the original function. I do all that work. This one was a bad example because it comes out nice. It gives me 0. But if I were to plug in this one, f of negative square root of 15 over 5, right? If I were to plug that into my calculator, let me do that real fast. And I'll round it to 3 decimal places. I get negative 13.824. So that comes out messy. Right? So often when we plug in these numbers, right, these values, we're going to get something that comes out messy for our height. And so that is how we find and identify our inflection points. And here we have 4 of them. Right, these are the x values, so you're going to have to do exactly this. Plug them into the original function to get the y values. All right, so you have quite a bit of work for this section, 3.2. So again, get started early. And if you want to see any specifics, again, make sure you're very specific in your questions when you send them my way, so I can know exactly where you're at and I know exactly what your homework, your problems are. Alrighty, so hopefully this was helpful, and keep your questions coming.